All right, in this video, we are going to talk about binary trees and prefix codes. So, before we talk about that, we need to talk about a directed graph. And a directed graph is a pair of sets, V and A, where V is a non empty set and A is a possibly empty set of ordered pairs of elements of V. So, if you recall the definition when we talked about graph, at the very beginning, it was a set of unordered pairs, right? We had vertices and edges. So with the directed graph, the pairs are ordered, right? In which the ordered matters. So the main difference is that you can think of a all the edges in a directed graph as having an edge, right? So with the ordered pair, whatever the first vertex is, that's where the edge starts, and then where the second coordinate of the ordered pair, that's where the edge ends. And you can indicate that by drawing an arrow on the edge. Okay. With directed edges, they are sometimes called arcs, right? And so that's why this second set is A for arcs instead of E for edges. I'll probably just end up calling them edges anyway. So, so this is a picture of a directed graph here. You can see, right, if you were on this graph, right, you have to follow the arrows, right? If you're at vertex A, you can go to B, and you can go to C. At C, you can either go to E or G, right? But um, you basically, as you're walking around the graph, when we talked about um, walks and paths and things like that before, uh, we could go in either direction. Now, right, we have to go in the direction that the arrow points on the edge. Okay. So when we talk about degree, things are slightly different now. We have basically two types of degree, the in degree and the out degree. And the number of arcs coming into a vertex is called the in degree of V. So here the in degree of H is 1. Here the, let's see, the in degree of E is 2, right? Because I have these two edges coming in. And the number of arcs coming out of a vertex is called the out degree of V, right? So H has out degree 1, C has out degree 2, F has out degree 2. Also, in the terminology for adjacent, we have to make a distinction, right? If there's an arc from one vertex to another, a vertex V to a vertex W, we say that W is adjacent from V, right? So here, A is adjacent from D, but D is not adjacent from A, okay? And then, again, in the same situation, when I have a vertex, an arc going from vertex V to a vertex W, then we can say that V is adjacent to W. So in this case, D is adjacent to A because the arc is pointing this way. But A is not adjacent to D. It is adjacent from D. Okay? So you have to make that distinction when we're talking about directed graphs. All right, and the application that we want to take a look at in this video, we're going to talk about rooted trees. So a rooted tree is a directed tree that has precisely one vertex R that has in degree 0. Okay, so no cycles. The edges are directed, and there's exactly one vertex that has in degree 0, and that would be this vertex here, A. Right, there are no edges that point into that. Every other edge has at least in degree 1 here. And this is a tree in the sense of that we talked about previously. Connected, right? No cycles. All right, that vertex is called the root of the tree. All right, a binary tree is a rooted tree with the additional property that every vertex has out degree 0, 1, or 2. So And those vertices without degree 0 are called leaves. So the leaves here would be D, E, and F because they all have out degree 0. The root is A, right? It has in degree 0. And you can see that the out degree of each of these vertices is either 0, 1, or 2, right? With A, it's 2. With B, it's 2. With D, it's 0. With E, it's 0. With C, it's 1. With F, it's 0. So this is a binary tree. The tree that we looked at before is not binary, right? Because B has out degree 3, and so does A for that matter. All right, so this is a rooted tree that is not a binary tree. This is a binary tree here. All right, in the application that we want to talk about in this section, then we're going to talk about encoding things, information. This is used in applications like compression algorithms for images and things like that in on computers. You can make images and other things smaller, like when you like a zip file that compresses that archives files and then compresses that archive down. Okay. All right, so an alphabet is just a finite set of symbols. So those symbols can be just about anything. Here we have the lowercase letters A through E as our alphabet. And here we have the numbers 0 and 1. And this is the one that we will deal with in this section. All right, a code is a set C of sequences of elements of A, where A is an alphabet. And the elements of the code are called code words. So for instance, right here, I have this code, CAD, BED, DAB. That's an example of a code for the alphabet A, B, C, D, E, right? So it's a set of sequences of elements that come from your alphabet. Here I have a code consisting of sequences of zeros and ones. That's an example of a code for this alphabet here. Okay. All right, so what we want to do is to take a piece of information and represent that piece of information using a code. And that process is called encoding. And what we want is for the code to be unambiguous and as efficient as possible. So, like I said, we will use the alphabet consisting of just two symbols, 0 and 1. And that is the application that is used in a lot of computer applications, right? Because information inside the computer is represented as sequences of zeros and ones. So if you have an image file or some other file that you want to compress down to a smaller size, right? And it gets written to the disk as a binary file, and that is just a bunch of zeros and ones, okay? All right. So as a first example, let's say that we want to develop a code to encode this following message. And the message is note, no notices. And instead of just representing a space as a space, I am going to represent it as an underscore. It's just a little bit easier to look at when it is an underscore there. Okay, so those really stand for spaces. All right, so I'm going to just try to generate a code for this message. I'm going to represent the character N by the code word 0, the letter O by the code word 1, right? The letter T by the code word 00, and so on and so forth, as indicated in this table. Okay, so here I really didn't put a whole lot of thought into picking these things out, and we're going to see that that's not a good way to go. We're going to wind up with an encoding that's ambiguous. So when we go to encode that message, you can see N is 0, O is 1, so that's that 0 here, and then the 1 right here. And then T, right, is 0, 0, so that's that 0. Let's see, no, this 0, 0 here, and then followed by that 0, 1 after it. Like that. and so on and so forth. So I'm just encoding each one of these characters using these code words. This is the string that I get. Now the problem with that is that this encoding is ambiguous. You can't decode it. Even if you have these characters here, even if you have this, right? Well, you receive this message, let's say, or try to read it from a disk, right? And you know these words right here. It can be interpreted in more than one way, and that's not good, right? So when you're reading this, maybe you think, oh, maybe this 0 and the 1 go together, and this 3 zeros go together, and then the 1 and the 1, 0, 0, and so on and so forth. If you do that way, right, 0, 1 stands for E, and then 3 zeros is a C, right, and so on and so forth. All right, so all of these, right, correspond to characters in my, or symbols, right, in my alphabet, but you can see that the message, the decoded message makes no sense, right? So there's, with this code, it's practically useless, right? You can encode things, but then decoding them, recovering that information, you know, is, who knows if that's correct or not. Like I said, even if you know this, right, even if you have this chart and you're following it, if you didn't know what the message said previously, well, you really don't know how to decode it properly. Okay, so that's a problem. So this is ambiguous. We definitely don't want this. All right. So the issue, it turns out, right, with that code before, is that you know, some code words, like this code word 0, they appear as initial parts of other code words, right? So like this 0 is a code word, and it appears as the first character here. So that kind of makes it impossible to tell, is it just 2 of these in a row, or is it whatever symbol this represents here? That's the issue that we're having with that code that we just made up. So a prefix code is a code C with a property that no code word in C is the prefix, or the beginning part, right, of another code word in C. All right, and so you can see this is definitely not a prefix code because lots of things appear as prefixes, or the beginning parts, right, of other code words. But down here, this code, right, is a prefix code. Right, this 0, 0, 0, right, it does not appear at the beginning of any of these other code words, and you can check each one, right? 0, 0, 1 doesn't begin this doesn't begin with the 0, 0, 1, neither does this, neither does this, right? 0, 1, 0, none of these the other ones begin with 0, 1, 0. All right. And so this is a prefix code. And the advantage of the prefix code, right, is that it's unambiguous when you go to decode it. Has to be, you know, if you have this table of symbols and code words, then there's only going to be one way to decode an encoded message. So it is unambiguous, and that's good. All right. So let's take a look at a second example here where we are going to encode the same message, right? And it's no notices again. And remember, these are spaces. And so here is my prefix code over here. And you can see, right, check this and notice, right, it is not a, none of these, right, are prefixes of the of any of the other code words in there. So this is a prefix code, and then we can go ahead and generate the message encoding. Okay. All right, and so that's good, right? It's unambiguous. That means you could actually use this, right, without it's actually practical to use, right? There's not an issue with being able to decode it in possibly different ways. It's going to be unique, right? When we read through this, right, we know that it's basically every 3 symbols. That's a 0 right there. And you'll know if you read too far into the code because you'll wind up with a code word that's not in the previous chart right here. Okay, So the downside is that the length of the message has increased, right? It's gotten bigger. And what we want to be able to do, though, is find the most efficient prefix code for any given message. That's what we'd like to be able to do. And it is possible to find a shorter prefix code for this message that we've encoded right here. The idea is to use shorter code words for symbols that occur most frequently, right? So if you're if you have a character that occurs many times, right, within the code, then you can just use a shorter code word for that, right, and that will save you some symbols in there. All right, so to do that, right, what we're going to do is for a given message that we want to encode as a bunch of zeros and ones, well, what we're going to do is build out a weighted binary tree. All right, so a weight in this application is just a non-negative integer, so 0 or bigger, right, and also an integer. And a weighted binary tree is a binary tree, like we talked about before, whose leaves are labeled by weights. Okay, so only the leaves, right? Remember, those are the vertices without degree 0. So those are labeled by weights. And then the weight of a binary tree is denoted by W of t, right? And it's given by this formula. So this would be the sum over all of the vertices B in the leaves, so all of the leaves, and the sum would be of the length of the path from the root to B times the weight of B. All right, and so you would multiply all those out and then add all those up for the leaves. Okay. So as an example, let's say we have this rooted binary tree, weighted binary tree, right? You can see that the leaves have been labeled with the with weights, right? And the root is up here, okay? And so to calculate the weight of this binary tree, what I would do is for each leaf, right? There's 3 leaves, this one, and this one. The length, right, for this leaf is 2, right? 1, 2 times its weight, so 2 times 3. So the length of the path from the root down to the leaf times its weight. And then for this leaf, it would be 1, 2. That would be the length of the path from the root down to that particular leaf, times by the weight of the leaf, which is 2. And then for this leaf here, the length of the path from the root down to that leaf is 1, and then times by the weight. All right, and so we get 6 plus 4, which comes out to be 14. So the weight of this weighted binary tree is 14. What we're going to do is generate a weighted binary tree for these for the character or symbols that appear in our message, and the weights are going to correspond to the frequencies with which the symbols are used, right? And the edges are going to be the number of symbols in our alphabet that we're going to use, right, to encode each of those. So what ends up happening is that this weight is actually how many symbols are going to appear when in the encoding of the message that we want to encode. And so what we want to do is to make this as small as possible. Okay, we want to make the weight as small as possible in this tree. All right, one other bit of terminology before we get started. A multiset is a collection of elements with repetitions allowed. I remember when we're talking about sets, regular sets, we don't repeat elements, but with multisets, we do. So for instance here, this is a multiset. It has 2 occurrences of the integer 2, 1 occurrence of the integer 3, and 2 occurrences of the integer 4. So we can repeat elements in a multiset. All right, and so as I mentioned previously, what we want to do, right, to find these efficient prefix codes is to find minimum weight binary trees. So if you're given a multi-set of weights, all right, so a multi-set of weights in there, remember those are non-negative integers, and they can be repeated. A minimum weight binary tree for the multiset is a binary tree whose leaves are labeled by the elements of M such that the weight of T is minimal. Okay. All right, so there is an algorithm that allows us to find a minimum weight binary tree for a given multiset, and that's called Hoffmans Algorithm. So in order to find these efficient prefix codes, well, what we're going to do is to look at the this Hoffmans algorithm, right? And it's going to generate a minimum weight binary tree for us, and then we'll be able to read the code words, right, off for each symbol off of the minimum weight binary tree. Okay. Okay, so in Hoffman's algorithm, what we're going to do, right, and we're going to start with a multi-set of weights. All right, so that's, again, just a list of non-negative integers. And what we're going to do is take the 2 smallest weights that are in there, right? So the 2 smallest numbers that are in the multi-set, and we're going to make a little tree that looks like this. All right, so this tree is going to have one vertex, all right, of out degree 2. That's this one right here. And it's going to have 2 leaves. Those 2 leaves are going to be labeled with the 2 smallest numbers in our multi-set, here and here. Okay. And then what we're going to do is label this vertex of out degree 2 with the sum, right, of these 2 numbers. So whatever number this is, whatever number this is, those are the 2 smallest numbers. And then we're going to label the this vertex up here with the sum, whatever it comes out to be, W1 plus W2. All right, so that's how we will start. In step 2, right, of Hoffman's algorithm, what we're going to do is select the 2 smallest weights that are remaining in M. All right, so once we build that first little part of the tree, right, we are going to again, repeat what we did in step 1, and we are going to take the 2 smallest weights. All right, and then we are going to repeat what we did as well, right? We're going to add that tree, right, to the, or this little bit here, same thing that we did before. We're going to label those 2 bottom ones with the 2 smallest numbers, and then we're going to label the top with the sum as well. Okay, so that's essentially the same thing that we did in step 1. All right, now the catch is that if you have one of these leaves in the tree with the same number of the one that you just added right here, right, so this and this number match, then what you're going to do is sort of attach these trees together. You're going to kind of merge them, right, into one vertex. So these 2 are going to get merged, and it's going to look like this. All right, so if you find that this, when you add the 2 smallest weights here and then label this vertex of out degree 2 with their sum, if it matches any of these leaves in here, you're going to merge it right onto there. Okay, so all right, and then the third step, right, is to check, hey, is there still one, is there still more than one element in the multiset, right? If so, what you're going to do is go back to step 2, and if not, then there is a minimum weight binary tree for the original multiset. We are going to be altering the multiset, right, every single time. What we're going to do is in the multiset, when you add these weights in here, like this, then what you're going to do is cross out those two smallest elements in the multiset, and then add in this weighted one up here. Okay. All right, so those are the basic operations in Hoffman's algorithm, and it's a lot easier to kind of see everything in action. So let's do that. Okay, so as an example, what we want to do is to use Hoffman's algorithm to construct a prefix code, right, for the message note no notices. That's the one that we were doing before. All right, and so what we would do is analyze the frequencies of the characters in the message. All right, so we can see here the N occurs 3 times, right? The O occurs 3 times. The T occurs twice. The E occurs twice. The space occurs twice. The I occurs once. C occurs once. And S occurs once here. Okay? And so our multiset would be this multiset right here. So this is the multiset that we are looking at. All right, so that is the multiset that we would start off with. So we're given that multiset. So for each, each message that we want to encode, there's going to be a different multiset. But here's how you get the multiset, right, by looking at the frequencies. All right, and then now we start off with Hoffman's algorithm. So Hoffman's algorithm says take the 2 smallest numbers, right, in your multiset. That's this one and this one. And make a little tree, right? Put these as the leaves in this weighted binary tree, and then label the top vertex with their sum, right? So 1 plus 1 is 2. So we would label this top vertex as 2. All right, and then we would also alter the multiset here, right? So we're going to cross those 2 ones out, the 2 smallest numbers. All right. And then we are going to add this 2 into the multiset. So we had 2 3s. We still had 2 3s. We had 3 2s, and so we added this extra 2. So you can see now we have 4 2s in here. We crossed off. We had 3 ones before, but we crossed off 2 of them. So now this is what our multiset looks like. Okay. And this is what our tree looks like. All right, so now that was step 1, right? What we've done, and then in step 2, right? What we would do is attach, this. If there are any other leaves of any other parts of this tree that had a 2 as the weight on the leaf, we would merge those, but there's none in this step. Okay. Looking at our multiset, right, we can see that we have more than one element here, right? So we would repeat what we did there before. Okay. Let me see. Oops. Yes. Okay. On to the next step, which is right here. So now this is what the multiset looks like after the previous step. The 2 smallest numbers are 2 and 1, right? So what we would do is pop those off right here, right? And we would make another small tree here with 1 and 2 as the weights on the leaf. And then we would label this top one with a vertex with the sum. 1 plus 2 is 3, okay? All right, and now in step 2, we can see that there was this situation, right, where we had one of the leaves over here was 2, right, weight 2, and then one of these vertices of out degree 2 had out degree 2 that matched, right? So these match here. So one of the leaves over here match this weight of this top vertex here. So what we're going to do is merge this. So this is going to get merged over here. All right, so it would look like this. Okay, so you can see what I did, right? This whole thing got moved over here. I merged it with that too, and that's this little part right here. You can see I still have the weights of the leaves with weight 1 in there, but now I no longer keep that weight on that vertex there. Okay, so I just erased that one. Okay, and then in terms of the multiset, right, that is crossing out the 2 and 1, right? Those are the smallest two. And then adding this 3 back in, right? And so the 3 that I added back in is one of these 3s right here. You can see I had 2 3s before, now I have 3 3s and 3 2s. All right, our multiset has more than one element, and so we go back to step 2. All right, so in step 2, I'm going to look at the 2 smallest elements again and make this little tree, right? The leaves have weight 2, and then this vertex of out degree 2, it gets labeled with a 4. Okay. You can see, so now this is really not a tree anymore; it's a forest, right? Because it has 2 different components, and there is no merging on this step, right? There's no place I can merge. There are no this 3, right? To merge this this piece over here, I would have to have a leaf that on this tree that had vertex that had weight 3, but you can see I don't have that. And likewise over here, to merge this one, I would have to have a leaf with weight 4, and I don't have that either. So that's it. There's no merging in this step. Again, I cross out the 2 lowest weights, the 2 and the 2 here, and then I add a 4 in. So this is now what my multi-set looks like, with the 2 2s crossed out and a 4 added in its place. Okay, next step is to take the smallest 2, right, in the multi-set and make this little tree over here. So here's a little tree with 2, 3, and then the upper node, right, our upper vertex is degree 5. All right. And on this one, you can see that there is some merging that I could do, right? I can take this piece over here, that upper vertex is labeled with a 3, right? So what I can do is I'm going to merge it with this piece over here. So I'm going to take this whole piece and just tack it on to this vertex right here. Sometimes you can do more than one, and you can see in this case that's the only one that we could do. All right, so in the next slide, you're going to see this piece get moved over here, like that. All right, so I got attached right here. Again, I erase the 3. I no longer need it because it's not one of these top points. All right, so I've done the merging, and then I still need to cancel out, cross out this 3 and the 2, and add that 5 back in here. All right, so now that's what my multi-set looks like. All right, next step then, go back to step 2. I pick the 2 smallest elements of my multi-set, make this tree here, and you can see I have the leaves are labeled with 3, and then I label the top vertex here with the sum, right, 6. All right, and then I try to merge anything that I can. I can see there's nothing, right? There's no leaves that have a 4, a 5, or a 6 anywhere in this. So there's no merging that can be done. All right. All right, so next up, cross out the 2 smallest 3s and replace, put back in the sum, right? The label of the upper vertex in there. So now that's what my multi-set is looking like, which is really just a set now, right? All right, and next step, same thing. Pick off the 2 smallest weights, 4 and a 5, add them over here, right? And the upper vertex gets labeled with a 9. And then I look to do any merging that I can, and you can see that I can do some merging, right? In fact, right here I have an upper vertex labeled with a 4, and so I can tack that on to a place where the leaf has weight 4 right here. So this part of the forest is going to get merged over here onto this. And then likewise the 5. Here I have one of these upper vertices with the label of 5. I'm going to merge that over here where with this leaf whose weight is also 5 because they match right there. All right, so in the next slide you're going to see this get merged here and this part of the forest get merged right here. All right, so that's what it looks like. Cross these off, the 5 and the 4, and then add the 6 back. Or add the 9 back rather, sorry. Okay, and then in the next step, pick off these two, the 5, oops, I forgot to update that. That should be 9, 6 here, sorry. So this should be 9, 6. So I pull out, let me just fix it really quickly here. It won't take me but a second. All right, so here's the part I get over here, and I label the upper vertex at the 15. And then now I look to merge, right? And you can see there's definitely some merging that I could do. In fact, I could tack this piece on over here, right? Because the root, right, of this part is labeled with a number that's equal to one of the weights of the leaves down here, and likewise over here. All right, that should fixed. Okay. All right, so in the next slide, you're going to see this whole component get merged onto this vertex here. This component's going to get merged over here. All right, so that's where the 9 got merged. That's where the 6 got merged. All right, and so this is what the now tree would look like. Okay, and then cross these out and replace it with the sum. And now in step 3, right, we can see that there is only one number right left in the multiset. And so we stop there, right? This tree is the minimum weighted binary tree for the multiset, okay? And so this is the output, right, that we want. So the next thing, right, to do, right, and that's Hoffmans algorithm, okay? So Hoffmans algorithm will generate this. And so what we're going to do is now use this tree, right, to generate our prefix code, okay? So a couple more steps to doing that. So the first thing would be to label the edges with 0s and 1s. This is what is actually called a full binary tree, right? Because there are no vertices without degree 1. It's either 0 or 2, right? And so what you would do is label, like for instance, this root vertex, it has out degree 2, so you would label one edge or arc with a 0, the other with a 1. Same thing here, right? Go to each one of these vertices of out degree 2, label one of the arcs with a 0, the other arc with a 1, and so on and so forth. And it really doesn't matter how you do it. On this one, I just put 0s on the left and 1s on the right, which just seems to kind of make sense, right? But you actually could be kind of inconsistent about that. Although, if your goal was to implement this in an efficient way, you probably wouldn't. You want to be more consistent. Okay, so that's number one. Label all of the edges of the weighted binary tree with zeros and ones, right? All right, and then what you're going to do next is label the leaves of the weighted binary tree with the characters in the message. And you want to do that so that the frequency of the character matches the weight of the leaf. So for instance, right here, we can see that N, right, matches, has a frequency of 3, right? So we're going to label one of these of 3 with an N, right? And then the other one with an O. And it really, again, does not matter about which one you do. You could label this one O and this one N, or vice versa. But if you again, wanted to do this efficiently, right, you probably would break the tie by, alphabetical order or some other similar situation like that. Okay. So that's what I'm going to do. So I'm going to put an N here, an O here, and then the T, E, and the space are going to go, one of them's going to go here, one's going to go here, one's going to go here. And then for the ones, the leaves that have ones as the weight, I'm going to put an I, a C, and an S there. All right, and so that's what I've done. You can see here in the next slide. All right, and so now you are ready to read off your code words. So the code words, right, you're going to generate those by writing down the edge labels, right, that appear on the path from the root vertex down to the vertex labeled by the character. Okay, so for instance, if I want to know the code word for the character N or symbol N, right, then I am going to start up at the root up here and write down the labels as I go to the path. Remember, this is a tree, right? And so there's a unique path, right, from the root down to N. So it would be 1, 1. And then the code word for O would be 1, 0. The code word for T would be 0, 1, 0, right? And so on and so forth. Okay. So again, you might say, well, wouldn't it matter if I did this in a slightly different way? And it would give you different code words for sure, right? But the encoding would be as small as possible. It would still use the same amount of characters. It would be the shortest one. Okay. All right. So now that we have our table of characters and code words, then it's really easy matter to encode, right? Because we just look those things up, right? So for an N, we have an 11. For a O, we have a 10. For T, we have 0, 1, 0, right? We put all those together, right? And then here's our message, our encoded message, okay? And now this is the most efficient one possible if you look at it, though, right? If you remember example 2 that we did, that used three bit code words, right? Every code word was a sequence of 3 zeros and 1s, right? And so we had 3 times the number of messages, or times the number of characters in there, which was 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? And so that was let's see, that's not quite right. see here. Yeah, 15, and then so 15 times 3, I guess it was. And so if you look at this one, right, if you look and compare this one that we had way back here, is what I'm trying to get at. I could have sworn I got a different count before, but oh yeah, I remember what that was. So yeah, if we look at yeah, so that was 45. So this example used 45 code words, right? Because we had 15 characters. We had each one of those corresponding to 3 bits, right? 3 zeros or ones. So that's 45, right? If you look at this code, which is the smallest one possible, right? The one that we generated, or the smallest encoding possible, it actually has 44 bits in there, right? So it's really only smaller by 1 bit in this particular case. But don't let that throw you off, or say that this is not a good method, because it's the smallest you can get. We have really small code words here because you can already see that going through the example takes a little while. So you can imagine if you're encoding lots and lots of things, like a huge image file or something like that, then where the gains would be significant, right, for making it as small as possible. So or so a really long text, which is the kinds of things that you would want to compress and make as small as possible anyway. Okay, so the longer it is, the more advantage you're going to gain when you compress. Okay, so it's not totally. Don't say this is terrible because all we did was save off 1 bit, but that is a little disappointing. But that's the smallest that you can get out of this. Okay. All right. So one other thing that I want to mention here is this tree also helps in decoding, right? If you want to decode a message, and then basically what you would do is have this little tree, right, in here, and then you can follow the tree when you're reading along in the code words, right? So like I'm reading 1 1 1 3 ones and 3 zeros. What you would do is start at the root, right? And then you start at the root, and so it would be 1 1, boom, I'm right here, and you would write that down. So you would know, hey, that corresponds to an N, right? And then you would start here, 1 0 0 1. So 1 0, right, would correspond to a 0. And so each time you would write that letter down. So that's what you would do. Just go over the digits, right, and let the digits choose which side of the tree that you go on. When you hit a leaf, you write down that character, right, and then go back up to the root, and then follow that process over and over again. So it would allow you to decode efficiently as well on that. All right. Okay, so that is it. In a later video, we will talk about some of the issues with the correctness, proving that this does give you, in fact, what you want. All right.